Welcome to the next conference on geometry, topology, group actions, and singularities on the Americas. I'm sure that we have very interesting talks over the next few days. And our first speaker this morning is Professor Bernardo Uribe from the Universidad del Norte in Colombia. And he will talk about Pontrjagin Duality on multiplicative gerbes.
Well, good morning, everybody. Ernesto, Ludmil not here, Steve, well, everybody from the IMSA, thank you for the invitation. Let me open up with this project that I finished right before the pandemic started, so I haven't been able to explain it. It has many words on the title that I need to explain one by one to see what is that I mean. So let me first state that this, it's not, and yes. So this is a project that I started with some students many years ago, and I was doing it with finite groups, and then later on I managed to do something for continuous groups. So what is the idea? The idea is that I will first of all explain the finite group case. So all these words that I mentioned, multiplicative gerbes, it has a counterpart in finite group case, which is the twisted Dirichlet double, and how it's related to pointed fusion categories. And I will tell you what is the classification and Morita equivalence of these gadgets. And then I will go to try to explain how could I, or how did we try, what is our proposal, to look at these things whenever the group is continuous. It's Lie or any continuous group. So the idea is that our objects here are going to be the symmetries. So our quantum groups will be the appropriate symmetry groups, and of course you could start with Hopf algebras and their generalizations. Importantly here is that we need to take into account the Young-Baxter equation. So since Andres is here, and you need to see that this train here in the middle, you can move it to the left, and then the two things topologically should be equivalent. But when you do it algebraically and you do this movement, which amounts to cross the strains here, you can do it this way or you can do it that way, and these movements should be equivalent algebraically. And this movement, you should think of it as some map in your algebra across the algebra that is shifting them. So good. So the quantum integrable group is many words here. It's a quasi-triangular Hopf algebra. But let me just go to this very beautiful idea of Dirichlet. If you have any finite dimensional Hopf algebra, for the time being, you may think that is the Hopf algebra associated to a finite group, either the variant or the covariant. And then you can just take since it's finite dimensional, you can take the dual. The dual is also a Hopf algebra. And the point is that once you get the algebra and the Hopf algebra together, there is a very canonical or simple way to define this R matrix, which is somehow the way you just shift the two strains that I just said before, and then in a very simple and general way, then one can define such R matrix that satisfies the Young-Baxter equation, thus giving many solutions or many examples of the realization of this Young-Baxter equation by just starting simply with a finite dimensional Hopf algebra. It's a very nice, beautiful construction and idea. So if you see it coordinate-wise with a finite group, so I'm taking the Hopf algebra of a finite group, and then it's the dual, and I'm just giving you all the structural constants of the Hopf algebra. So it's an algebra, and then you can see the product. But this product, as you might see, the group is acting on the other by conjugation. The natural coproduct, identity, co-identity, the inverse map here. And it's just simply copying from what we did before. This is the R matrix. What is interesting also is that you could twist it. There is a way to somehow put more cohomological information into the picture so that the final construction becomes a twisted version of the original one. A lot of formulas, but somehow you have to twist the product, you have to twist the coproduct, and the twisting need to be all over the place, appropriately set up, and the point is that at the end there is an associator here that depends on a 3 cocycle with values in C star for this type of algebra. But all this information, all this omega, beta, mu, you can just wrap them up in a cocycle in a specific simplicial set. Namely, you take G acting on G by conjugation, and you get an appropriate cocycle here, and this all the information that you need to put on the twisted Drinfeld algebra is located in just a simple cocycle. You simply do a pullback of a map, and then the whole information is there. The point of this is that you could take the representations of this twisted Drinfeld double, and it becomes a non-degenerate braided fusion category with a choice of a spherical structure. Many words, but it's a very concrete object with many properties. And when you somehow see it as an extended Chern-Simons field theory, namely you want to somehow associate, you forget the one, you used to think that you have two-dimensional manifold and Bordisms with three-dimensional manifolds. But if you want to try to extend it to a point, to go not only three-dimensional and two-dimensional, but also lines and points, well, in this setup, you can go and associate to the circle this representation category of the twisted Drinfeld double, and it somehow collects all the information. And from this, you can reconstruct the whole functor just by knowing somehow this twisted Drinfeld double associated to the category. Of course, you might think that this twist here is what is entangling in the three-dimensional manifold to measure the information of the Bordism. When I was doing my PhD, this was information that somehow Alejandro Adem was interested at the time. That if you take a look at the isomorphism classes of representations of this gadget, whatever that is, you could look at it in a parallel description or separate description as the twisted equivariant K theory of the group whenever the group acts on itself by conjugation, and as a module here you can split it in this way as the object, and of course there is a way to endow this with a product structure just doing a pull-push argument that it turns out to be equivalent to the representation of the twisted Drinfeld double. So there is an underlying object that is even below that is a pointed fusion category. It's a very simple gadget on which you just simply take vector spaces, finite dimensional, graded by the elements of the group. The tensor structure is just tensor structure in the vector spaces, and you put also the group structure in it. And then you collect information of the associator by just the 3 cocycles. So this is a simpler, say, object than the twisted Drinfeld double. And the point is that this type of module categories, you think that this is some sort of an algebra, generalization of an algebra. Of course, this has modules, and you just simply take the idea of what is a module over an algebra, and then you bring it to fusion categories, and it's just a category, and you have a tensor product, and of course you need to control the associator with some pentagon axiom, and of course, and all the higher structures that are necessary. What is important is that for you to have a module structure of this category, you need the irreducible ones is an orbit type, and some information here over the orbit type that equivariantly trivializes the cocycle. That is very important. So if you want to have a module, you need to trivialize the cocycle whenever you pull it back. Otherwise, you cannot get a module. The many important things of having this description, because it's a very simple one, you may think is that it's a kind of a categorization of the group algebra, because you have the group and then you have just vector spaces glued to the elements of the group. you can do many nice things algebraically. You can take the endomorphisms of a module with respect to the pointed fusion category, the fusion category, and whenever both the category and the module are semi-simple, if you do it twice, then you just recover the original category. This is very important for the duality procedure. Moreover, since we can mimic what we do in algebra, you can get the center associated to this tensor of this fusion category. Just simply the way you could do it in algebras. And nice thing is that by doing this center, then it's very simple to define a braiding in this category. So this one is moreover, it's not only a fusion category, it's more also a braided one. And what happens is that one has this very nice canonical, well, this isomorphism, which allows you to think that instead of thinking of the twisted differential double as the object, we should think that this is coming from the center of a fusion category. So we can go one level down and think of it as the appropriate object is the twisted fusion category associated to vector spaces created by G. So no, it's just these are the strings. This is what is below the strings. You need to do the strings of this to get this. If you want to, yeah, homotopically they are the open ones. But I was just thinking that this is just homotopically contracted to a point. So this is just points. But yeah, homotopically they are the open ones, and then. Sorry, I went back. And so, a very important result is associated to this definition of Morita equivalence. Yeah, of course, we could think that Morita equivalence is equivalence of module categories. Alternatively, we could simply say that two of these categories are Morita equivalent if there is a module category of one such that the endomorphisms of one with respect to the other brings me the original one. But the nice result of Ettinghoff, Nitschik, and Ostrich is that two of these fusion categories are Morita equivalent. If they are Morita equivalent, it's easy to show that they have equivalent centers, braided. But the interesting thing is the opposite, that if the centers of the two fusion categories are braided equivalent, then you can go back and you can get the Morita equivalence of the two original categories. So it's a very amazing theorem, and you need the braiding to go back. Somehow you don't get this type of things in algebras. Good. So since we know that the center of this small fusion category is the representations of the twisted different double, we can get this very nice result. Take here the twisted different doubles. The representations are braided equivalent. If we know what is the Morita equivalent class of these types of fusion categories. So one question that one could ask, of course, is since this is already what's happening at the circle for the extended Chern-Simon theory, then we know that whenever these two categories are Morita equivalent, they will give me equivalent extended Chern-Simon theories. So one question is to what type of groups together with twistings are equivalent. And so this is some work that I did in 2016. It took me some time because I wanted to do it so explicit that I needed to take explicit model of the groups, of the cohomology. There were some results already in the literature, but they were not explicit. They were in terms of spectral sequences, but I was lucky enough to find an explicit, simple model for all the cocycles so that I could give a complete understanding of whenever two groups with twistings are Morita equivalent. And the point is that for those two objects of these types to be equivalent, you need two different groups. In some sense, this is just a notation to say that this one G is an extension of K by A, and this is the cocycle that controls extension, and of course K is also acting on A. Meanwhile, the other one needs to be an extension of K by the dual of A, so A will be here abelian, And there is a way to explicitly say how the group and the cocycle intertwines to define the Morita equivalent one. I'm just giving you formulas here, but let me give you perhaps a diagram. So the point is that what is important is that there is a way first to trivialize. Well, let me put it in a diagram perhaps. Perhaps it's easier this way, yeah. This is just schematically when our two groups, a group with a omega and a group with another omega equivalent. Let's just recall that this gives you a cohomology of the third cohomology of this group with coefficients in C star. This also gives you a third cohomology element in the group G with C star coefficients. So this is more or less like diagram. It looks like a T-duality map. Of course, it is what it is. It is a T-duality construction, but in the sense that you need to do in the appropriate category. For the T-dual, say this is a manifold here, and you have some principal bundles, but in this one, this is a group, so we need to do it one level higher, keeping in mind that the bottom space is a group.
And here, of course, this is
Yeah, exactly. So this is at the level of the points. There is no braiding because it's on the center. But the point is, yeah, the idea is that these objects are easier. It's just a group and a cocycle. That's what it is. There's nothing else. With the center, you need to have the braiding, but everything is reconstructed out of this one. So, of course, one could try to see what is the isomorphism classes as braided fusion categories of the center. But that's, I think, more complicated than to try to construct This is as explicit as possible, and therefore it's easy to make formulas out of it. That's what is nice about it. So the idea is that here we have two extensions of groups, one by an abelian group, the other one by the dual group, so homomorphisms from A to C star. But the information that controls this extension is included in the cohomological class of the partner, and vice versa. The one that constructs this extension, this is a second cocycle, is here with some extra information, of course, coming from any twist that can come from the bottom part. So the extension is controlled by the twist, and the extension is controlled by the twist. So they flip information now that we have more place to move information around. And this is all the possibilities. In particular, the size of these groups have to be the same, no? And this is infinite group theory. Just to give you some sort of an example, of course, if I want to know whether the Morita equivalence classes for the size of the group 4, there are only two groups that matter, and of course I need to take the automorphism group acting on the cohomology to detect what are all the types of cohomology classes that could give me same pointed fusion categories. And this is the list of the pointed fusion categories up to isomorphism living in C2 square, and these are all the pointed fusion categories living on C4. Of course, what I'm doing here is I'm classifying the fourth cohomology or the third cohomology with C star coefficients up to automorphism. But the point here is that in this line, these two become Morita equivalent. So this is isomorphism classes, but in this horizontal line are Morita equivalent, and that's what I'm putting here. This simple vector category is Morita equivalent to this one. It's not isomorphic, it's Morita equivalent. That their centers are going to be isomorphic. Of course, you can see that what is measured, the extension that is non-trivial is put now in the cocycle, the non-trivial extension. The twisting, so the twisting of the group is mapped here to the twisting of the class. Geometrically would mean that if I do this, the Chern-Simons theory associated to this one, I need to twist already the whole modular space using this class. So for the next case, for the next case, which is interesting here, is that of course I'm doing the same thing, but I want to highlight that there is a class in Q8, the trivial one, a class in the dihedral group, and a class in the C2 to the cube, which produce Morita equivalent fusion categories. So the centers would be the same. So either with Q8, D8, or C2 to the cube. Of course, what is underlying is that the appropriate object is neither the group or the cocycle, is the intertwining of the group and the cocycle. So the group and the cocycle, you could have different projections in Q8, D8, or C2 to the cube. And you may choose either one for your calculations too, depending on what you want to do. So you can count them. And so the explicit formula for the Drinfeld double, you see, this is so bad. I was trying to do it 7 years ago, and I tried it with the wrong formulas at the beginning, then I got stuck, and I could not do it. Then I had these explicit cocycles, and then two Chinese physicists wrote it very simply, the complete direct isomorphism, but of course it had to be simple. I was close, but I didn't notice. Nevertheless, so they wrote a very nice paper on electromagnetic duality, and this is the explicit map. Of course, you don't see the twistings here, but whenever you want to show that it's an algebraic isomorphisms and a braided out, then the whole.
It's only when they have cancelled out.
They are not here, but whenever you try to prove something, then you have to split them. So it was the easiest of the easiest thing, but of course, if you don't know the explicit formula, then you cannot construct the map, because then you don't know how to prove anything. Forward. So when I was doing these calculations, of course, from classical instruction of mine, whatever you can do for finite groups, you should be able to do it for compactly groups. So somehow there should be no obstruction to simply do the same. And so my motivation was that. How do I do this for continuously groups? And how do I construct a generalization of this point diffusion category called vect G in the finite group case to the Lie group case? So in the compact Lie group case, this functor from the Bordism category associated to the Chern-Simons theory is the category of positive energy representations of the loop group with energy k, if k is a level that lives here. That's the object that goes to the circle, and there is this question, what goes all the way down to the point? There are some options written by many people, and Enrique is one of them. And I thought that what I did could be a proposition or an option to build something on the point. Difficulties arose quickly because it was not clear what was the appropriate fusion category to put there. But so my idea was to extract all the topological information that I could from the algebraic setup here for a finite group, to extract it and to put it in the universe where at least I know things would go well. And so the idea is to start with, first of all, shifted U1 bundles over sets or spaces better, and then do all my calculations in there. And so I had to propose some objects, and this is what I'm going to try to do. So the underlying category where I will try to do all my calculations is going to be manifolds that are endowed with a gerb, with a U1 gerb, or in other parlance, it's just U1 shifted 1 principal bundles. Since this is a billion, we can move it up and down as much as we want. If you just put just like this is a principal U1 bundle, but we shifted 1 level up, and then we have a groupoid there. Groupoid, so you might think this is just a manifold groupoid, and this is a groupoid with one object at U1 automorphisms. And we just study those. This is the category of these manifolds with this structure. The class that defines it is a gerb. Like the Chern class of a line bundle, we have a gerb here, a Dirichlet class. So my original idea was to study these objects as they are, but then the construction explicitly were complicated, so we decided to use a model for cohomology of continuous groups that was proposed in the 70s by Graham Siegel. And this is a very nice model for cohomology of topological groups. Even though the homological algebra structure behind it is not still completely built. Namely, I will take a model, specific model constructed by Graham Siegel to understand the topology of a group. So the idea is I'm going to work in the category of contractible, locally contractible house of topological abelian groups, so it's as wide as possible. And this exact sequence, you should think of it as an exact sequence in this category, not only that this is a space and a principal A bundle, but it's an exact sequence of topological groups. Because you have abelian topological group, you can endow this universal space with a group structure, and then you can take the quotient. This is normal, so this is also a group. So this is not only a principal A bundle, it's an exact sequence of groups that moreover is a principal A bundle. And then you can keep doing that, namely, this is a group, but it has topology, so it says it's not contractible. So you can do E of it because it's a group. And if you can do E of it, you can map E of A to the bottom, E of to BA, and then you can include it here. And you can keep doing it. You can keep doing it. You can keep doing it. And it becomes a very nice resolution of A in this category, but now all these groups are contractible. All abelian and contractible groups. So this is the main idea of Graham Siegel to understand homologically how we're going to construct cohomology with coefficients in A using this nice, very nice resolution of topological contractible groups. So then, having this resolution, one can define a cochain complex, and the cochain complex will be simply take any topological space for a compact we need and map it to here, and simply use the boundary map to define the cohomology, and this will be the cohomology of the space X with coefficients in this abelian group, like a shift cohomology type of definition. And of course, you just do some simple calculation in this case, and the mth cohomology is just simply maps to the classifying space here, the appropriate classifying space of the group, of course. And the zero cohomology is the one that is complex because it just maps like shift cohomology. But of course, sorry, let me go forward. But you can also do this simplically. The same type of attitude now. Simplically, you don't only have resolution to one side, you have also the simplician resolution to the other side, and then you make a double complex associated to it. And if you have, let me see, I think I went one forward. Oh yeah, of course. So you have a simplicial space, then you can just have this double complex associated to the both degrees, and you can simply take the total complex, and that will be the cohomology of the simplicial space with coefficients in the abelian group. In this way, one can define the cohomology of a topological group using the nerve of the category associated to it. And it is a very nice theorem of Siegel that in this universe, for a compact, complexly generated topological group, locally contractible, that I forgot there, that the H1 groups is what it has to be, so homomorphisms, continuous homomorphisms, of course, and that H2 is extensions, as what we would expect in the finite group case. And again, this is using the fact that the groups are topological. Any extension that you construct need to be topological. And what is also interesting is that the third cohomology of Siegel-Mitchison cohomology of this group with coefficients in abelian group A is the isomorphism classes of extensions of two groups. So what is that? Now I'm in the world of two groups. So two groups is a groups in groupoids, and so the groupoid here is simply no automorphisms, but the group structure is the group itself. And here you get the two group on which it only has one object, and the automorphism of the whole two group is A. And if you do isomorphism classes of extensions of two groups of these ones, so G naught on the left and A1 on the right, G naught on the right, A1 on the left, is classified by this H3. This is of course generalizing theorems of classical theories in finite group theory. Nevertheless, the proof of this is not so simple, because the structure to define extensions of two groups needed to be constructed, and this was done recently in some way by Schomer-Priest and categorically or in the algebraic setup by others before. Good. So we know more or less that we are in the right setup. So for example, whenever G is a discrete group and the group A is contractible, say the reals, or we can just take simple continuous cohomology chains. If the group on the right-hand side is discrete, then we can just classify the group on the left and then just take standard simplicial cohomology. What is this saying is that it incorporates all possible cohomologies that we know for groups. If it's a continuous group, there is continuous cohomology structure. If we can do classifying, but only matters when, and only works perfectly when this is discrete. But whenever we are in this grade of generality, you need to put Siegel-Mitchell cohomology. And of course, there is the type of Lindell-Hochschild spectral sequence that I will use. So, what is the category? So I'm going to take objects, Siegel-Mitchell gerbes. We just call them that way, but these are just gerbes modeled in the Siegel cohomology structure, namely maps from M to B squared A. Namely, these are just the principal bundle associated to it by the pullback, and this will be my objects, and then I just pull the whole machine to define morphisms and two morphisms, since of course the morphisms will be B1 and the two morphisms will be A, and we stop only at this second level of two morphisms, and we get a very nice two category on which everything is continuous. It has, of course, a monoidal structure, the most, as in gerbes or as in principal U1 bundles. You multiply the spaces and then you put back the principal bundles and properly tensor them. And a multiplicative gerbe in this structure, now is a simple gadget to define because it's whole homological. Well, will be, and one can simply, it's a multiplicative object in this category, multiplicative in the sense that we have a two category that is monoidal. And it's easy to show homologically that the multiplicative gerbes out of a fixed monoid, because of course we need a monoid structure in the space, is just simply classified by the third cohomology group. So again, equivalent as we were doing in finite group X. That's the whole idea of this cohomology. I'm just putting a lot of words here, but then what is a module? Well, we need the group, say, acting on a space. Moreover, we need some sort of cocycle that trivializes the original cocycle. And we can put all the structure that we could imagine so that we can bring topological group actions on manifolds. So again, this is just what is a representation. It's just generalizing the concept of a module category over the fusion category. It's just I don't have anymore a fusion category. I have simply a two category with a monoidal structure, and then I could just get the representations, whatever they are. These are the representations. If we think this is a group, a monoid is acting on a space, that would be in the category of homological spaces, but we have more homological structure. And of course, you can now have endomorphisms of these gadgets in the same way as before, just using the whole categorical structure. And whenever we understand endomorphisms, and that's the key point, we have such a category of endomorphisms, we have some, the objects, the isomorphism classes of objects is just some topological thing. And in the structure of the automorphisms of the identity, we have some cohomological information. And this is what we want to use. So we want to do the same duality that we did for finite groups, but we want to do them in this setup, in which we have less theorems, but we can do it all, fortunately, topologically. And so the idea is I start with an extension in topological groups. I want this to be abelian. And I'm going to take what are the cohomological classes here that I could somehow, using this endomorphism structure, how do I get another one, which will become dual in the Pontrjagin sense. So first of all, I need, of course, this group to be abelian, because I want to use Pontrjagin duality at the fibers, and I want the double dual to be itself, first thing. So this tension is for an abelian group. Secondly, I need that the cohomological class that it lives on G has to trivialize on S. That's the second thing that I need to do. Otherwise, I will not get a module This is the first abstraction for the module, and I write it here in the topological case. Why? Because otherwise, this K will not give me a module of the appropriate category. Secondly, I need this group to be normal, and the reason why I need it to be normal is because I need this home map to be K itself, so that the bottom thing is still K. And thirdly, I need that it dies in a specific place of the Lindow-Hochschild spectral sequence. And the reason for that is so that the dual group has a specific, is surjective to the group K. So all these conditions are set up here in the Lindow-Hochschild spectral sequence, but if I have an element of the cohomology of the group that satisfies some conditions, then I can construct a dual structure. And the dual structure is simply take the module, again, take the endomorphism category, and one can show that this, again, in this case is a 2 group, which is an extension of a dual group with respect to the U1 shifted 1. And the whole construction gives me another cocycle, and this cocycle lives in the third cohomology of the dual group. And this procedure, as is set it up, you do it again, and then you recover something isomorphic to the original one. So, of course, we put it here as a theorem, this thing, because this is the main construction that we are able to show that this is an extension. This group is an extension of this one by that one, which looks like the same. Look as in the group, in the final group theory case. And of course, it's the same diagram. I put the same diagram as before. It's just now everything is topological. But again, I cannot use the structure fusion categories to help me, so I need to do it more hands-on on the category of gerbes. These are 2 examples that perhaps is what Ludmil wanted to ask me, and of course one can cook more up, but and this I know. If I tell this example for the people that know might think, yeah, but this is obvious because several reasons. And nevertheless, it comes out of the structure. So if you have SU2, which is one of the most important examples for this Chern-Simons theory, and of course I'm not going to take any level because I need to choose the level appropriately so I could find its dual. I told you I need specific conditions for this, for the homological class to work. Or let's put it also here in the dual group. And so the idea is that if I have SO3, SU2, this is an extension by Z2. So the abelian group now is Z2. And then one can show that in this setup, SU2 with levels multiples of 4 is equivalent in this, well, it's not equivalent, it's dual, Pontrjagin dual to SO3 cross Z2, of course, with the Pontrjagin class generator here and the Stiefel-Whitney class coupled with this. So, yes, from Friedkopf-Minster elements, you could also read it behind it because the way it's done as you do it in the Lie algebra, you don't see it here, but then you need to incorporate all the twisting from the cohomology class, and then the error of not putting here, you need to put it here using the Stiefel-Whitney class, or either way. But of course, we were doing all this, and you can do any topological group that is not compact, no? And so the simplest case would be R3. So R3, but then you put this twist, which is just simply being by multiplying the 3 variables on the exponential. And then you take this Heisenberg group. And the Heisenberg group with the trivial twist is going to be equivalent to R3 with this twist. Again, one might think, well, no surprise, because this is a generalization of the finite group case. No, you just take Z2 to the cube, and then you take here the quaternions or the dihedral group, and then exactly the twisting for the Z2 to the cube is it looks exactly like this. But of course, one can cook up many more things now that we don't have the restrictions to be finite or compact, no, because any group do. In all examples, it's the same structure. The groupiness goes to the gerb, and the gerb brings the, yeah. It's just, the idea is, if one has the examples of the finite group case, this is easy to cook up. You know, the formula is what it is. What it took me sometimes, how do I build a machinery that allows me to say that they are equivalent, in what sense are they equivalent, or in what sense do they bring equivalent information? And that's why they needed to bring Siegel's cohomology to help me. And of course, then, now we can also calculate the centers of these monoidal categories, and if they are Pontrjagin dual in this universe, then their centers. Why am I doing it this way? Because then these are two groups, strict two groups. So I strictified the non-strict. So I strictify them, and when they are strictified, then these things are easier to define. And so whenever two of this information are Pontrjagin dual, then the centers are equivalent. And as I said before, of course, I would like very much to go backward, to go the other way around. That if I have equivalent centers braided in whatever universe this lives, that I could go back. But I don't know how to do it, because the way Ettinghoff and Strick do it, it uses heavily the finite dimensional structure that they have. And here I don't have any of that. Or maybe it's easy, just I don't know how to do it. And so, of course, what about these types? For the compact case, should be easier, I suppose. But what one doesn't want is to construct a map. So what it would be nicer that is somehow embedded in the whole categorical structure, that is just some sort of tautology. But of course, if one knows the groups, one can perhaps construct it explicitly. Forward. And so for the people that know this, well, this is what is exactly needed in Friedhoff-Stellman construction of the ring structure of the twisted equivalency theory of the topological group acting on itself by conjugation. And so if I knew, but which I don't know, what are the representations, or what are the objects on which these act, and to classify them by isomorphism classes, I would recover this twisted equivalency theory. But somehow what I have here is an object, a clear object, but I need to make it act somewhere. Maybe Ernesto has the answer, but of course, if I were able to do that with somebody, then the right-hand side would come automatically. We would get the isomorphism. If I have two different groups and two different cocycles that are Pontrjagin dual, the right-hand side will be the same. If we had this part, which I don't know how to do it. So what is the? So as I said, once I wrote the formulas for the finite group case, I completely thought this is possible to generalize to continuous groups, but I didn't have the framework. I didn't know what is the categorical framework where these things lying, so that one could bring all these very nice structures of pointed fusion categories or fusion categories that they're very robust to deduce theorems. But it didn't have it. So I went around somehow by taking all these ideas of finite group theory and put it into topological groups. Siegel's construction helped me, of course. But I went around to define the appropriate object, the appropriate centers, but I don't still have the representations of those things. And of course, this is lacking the fusion categorical structure appropriately defined, so these things somehow just flow. So, of course, this is what is called by the physicists electric-magnetic duality, because you just dualize and then you exchange the magnetic charge with the electric charge from one to the other. And what we've accomplished is that we know that they have equivalent centers, but in this categorical setup. We don't know how to go back, whether the braided centers being equivalent, that the multiplicative gerbes are equivalent. And of course, we haven't put either connections, which is, of course, one next step. Once you have the topological structure, then you can put the connections there to do it geometrically. But it was some sort of a proposal from me of trying to overcome the topological one. I'm still, of course, not happy with the result because Ernesto was reading the thesis of my student that tried to organize all this information, and it's just so heavy it's like going around to go to some result that everybody believes is true, but how do you prove it that it's true? So there must be a direct way that one can do it without all this going around. So this is a product of some papers that I did with myself and my students in the group, in the finite group case, and this one is still 2 years ago, and it's still trying to be published somewhere. But thank you very much.